A z-score tells us how far a value is from the mean measured in standard deviations. Essentially, it tells us context about a given value, right? Where does that value fall in the range of all values we're looking at? Is it below average? Is it above average? How far below average is it? How far above average might it be? To calculate a z-score, the formula is straightforward. You're going to take the value you're looking at and you're going to subtract the overall mean for the distribution, and then you're going to divide that by the standard deviation. Here's an example. I've laid out a vector of hypothetical test scores, and let's say we are the student that earned a 75. And we're feeling a little bit bummed because that seems low, but let's calculate the z-score. Let's see what that score is in context of our peers. So plugging in our formula, our value for x is going to be 75. We need to subtract the mean of all of our scores, so I'm going to use R's built-in mean function for this. And then we're going to divide that by the standard deviation of our scores. So again, using built-in functionality, we're going to use the SD function and pass it our scores. And then finally, we'll run our code, and we can see that our resulting z-score is 1.05. So what this tells us is a score of 75 is 1.05 standard deviations above the mean. In other words, we performed above average, and we could feel a little bit better understanding that maybe this was just a really hard test and we actually did pretty well considering. For comparison's sake, let's do another z-scores calculation. This time we'll do it for the student that got a 20. So their z-score is a negative 1.45. So anytime you see a positive z-score, that indicates that score was above the mean, and a negative z-score indicates it's below the mean. And again, it's telling you how many standard deviations above or below the mean. If we were to get a z-score of 0, that tells us we scored exactly at the mean. In this example, we saw the utility at contextualizing a score within a single distribution. But another useful feature of z-scores is it allows us to compare scores across different distributions. For an example of this, let's think about college admission tests. Two common standardized tests that students take are the SATs and the ACTs. And let's imagine we're comparing two different students, and one student took the SAT, the other took the ACT. So our first student, they got a 1250 on the SAT. The second student who took the ACT, they got a 36. Those are very different scores, and so if we were trying to do a comparison, it's really hard to contextualize those scores. So what we can do is we can calculate a z-score to see not just what their raw score was, but where did that score fall in the distribution amongst their peers? Let's do that work. So starting with our SAT student, they scored a 1250, and the mean score for the SATs is 1050, so we'll subtract that, and the standard deviation is 200, so we're going to divide it by 200. The calculation for our ACT student is they earned a 36, and we're going to subtract the mean for the ACT, which is 26, and then divide that by the standard deviation, which is 5. So let's run both of these calculations. And we get a z-score of 1 and 2. So both students performed above average, but we can see that student 2 performed slightly better. They had 2 standard deviations above the average, whereas the SAT student was only 1 standard deviation above the average. All right, so our raw scores of 1250 and 36, not really helpful to compare those two, but the z-scores just give us a much clearer sort of apples to apples comparison.